Building a finite element model typically begins with a strong form differential equation and the application of the weighted residual method. However, this requires a pre-existing differential equation for the system. In many complex structural problems, that specific equation is not always known or easily defined. A robust alternative exists in the work of physicist William Rowan Hamilton, who demonstrated that physical systems can be modeled using only their fundamental scalar energy definitions. This framework is known as Hamilton's principle. By utilizing this principle, we can bypass differential equations entirely and derive the exact finite element model for a 1D bar element using energy functionals. We begin with a one-dimensional bar element of length L. We define point loads at the boundaries, P1 at x equals 0 and P2 at x equals L. Across the length, we account for a distributed force, f of x. These loads cause the bar to deflect, a displacement we define as the variable u. To apply Hamilton's principle, we must now express these physical forces and deflections as two scalar quantities, external work and potential energy. External work is defined as the sum of the forces multiplied by the distances they move. This includes the point loads at the nodes and the integral of the distributed force across the length. Internal potential energy, or strain energy, is defined as 1/2 the integral of the stress times the strain over the entire volume of the element. Using Hooke's law for linear materials, we replace the stress term with the modulus of elasticity multiplied by the strain. Because strain is the rate of change of deflection with respect to x, we substitute the strain terms with the spatial derivative of u, resulting in this squared derivative. If we assume the deflection is constant across any cross-section, we can perform the integration over the area and reduce the volume integral to a one-dimensional integral over the length. The total energy state of the system is now expressed entirely as a functional of the deflection variable. We now apply the variation operator, the central action required by Hamilton's principle. This operator applies only to the unknown deflection variables within our energy equations. Within the strain energy term, we must take the variation of the squared spatial derivative. Applying the chain rule allows us to expand this term. The resulting coefficient of 2 cancels the leading 1/2 fraction, leading the variation of the rate of change multiplied by the rate of change itself. This completes the continuous variation statement, which serves as the starting point for discretization. We now replace the continuous deflection variable with an approximation, shape functions, n, multiplied by nodal degrees of freedom, d. Similarly, the variation of deflection is expressed as shape functions multiplied by the variation of the degrees of freedom. To factor out the degrees of freedom later in the derivation, we must first address the orientation of these matrices. Because deflection is a scalar quantity, it is mathematically identical to its own transpose. Taking the transpose of the variation term converts the column vector into a row vector, which aligns the dimensions for factoring. This step is necessary to separate the arbitrary variations from the physical properties of the element. We substitute these transposed matrix terms back into our global variation equation. A common variation term now appears across every part of the expanded expression. We can now factor out the transposed variation vector of the degrees of freedom, leaving the integrated energy and work terms inside a single set of brackets. According to Hamilton's principle, this entire factored expression must equal 0. The system is now divided into two parts, an arbitrary variation on the outside and the structural data of the element on the inside. Since the variation vector is arbitrary and unknown, it cannot be 0. This implies that the expression inside the brackets must be what equals 0. The first integrated term represents the stiffness matrix, K, matching the result obtained through the weighted residual method. The remaining terms are the generalized force vectors. Moving them over gives us the standard finite element form, K times D equals F. This confirms that we can arrive at the standard model using energy functionals instead of differential equations. This derivation shifts the focus from balancing forces at every point to evaluating the energy state of the entire element. This energy-based approach is particularly valuable for complex structures, where the governing differential equations are difficult to derive or solve directly. The same sequence of defining energy functionals and applying variations will allow us to derive models for more complex structural components, including beams. Hamilton's principle provides a foundational tool for finite element modeling, allowing us to derive the mechanics of a system starting only from its energy.